Before Niels Bohr entered the scene, the atom was already one of the most fascinating and troubling subjects in physics. Scientists knew that matter was made of atoms, but what those atoms actually looked like, how they behaved, and why they were stable remained deeply confusing. By the late 19th and early 20th centuries, physics appeared powerful and nearly complete on the surface, yet the atom exposed cracks in that confidence. The story of the atomic problem before Bohr is a story of growing tension between experimental discoveries and the limits of classical thinking, a slow build-up to a scientific crisis that demanded a radical solution. For centuries, atoms were little more than philosophical ideas. Ancient thinkers like Democritus imagined indivisible particles as the basic building blocks of matter, but these ideas were speculative and lacked experimental support. It was not until the early 19th century that atoms became part of serious scientific theory. John Dalton's atomic theory proposed that elements were composed of tiny, indivisible atoms that combined in fixed ratios to form compounds. Dalton's model worked remarkably well for explaining chemical reactions, but it said nothing about the internal structure of atoms. Atoms were treated as solid, featureless spheres, useful for chemistry but silent on deeper physical questions. As the 19th century progressed, new experimental tools began to probe matter more deeply. Electricity and magnetism became central areas of study, and scientists discovered that atoms were not as indivisible as once thought. Experiments with cathode rays revealed streams of negatively charged particles, later identified as electrons by J. Thomson in 1897. This discovery shattered the idea of the atom as a solid, indivisible object. If electrons existed inside atoms, then atoms had internal structure, and that structure needed explanation. Thomson proposed an early model of the atom to account for his discovery. In his picture, often compared to a plum pudding, the atom was a sphere of positive charge with negatively charged electrons embedded throughout it. This model had an appealing simplicity and fit some experimental observations, such as overall electrical neutrality. However, it raised new questions. How were the electrons arranged? What held them in place? And most importantly, how could such a structure remain stable? At the same time, classical physics seemed fully capable of answering almost any question. Newton's laws described motion with great precision. Maxwell's equations unified electricity, magnetism, and light, and thermodynamics explained heat and energy. Many physicists believed that with enough refinement, classical physics could explain everything, yet the atom began to resist this confidence. When scientists tried to apply classical laws to atomic systems, contradictions quickly emerged. One of the most serious problems involved radiation. According to classical electrodynamics, an accelerating electric charge should emit electromagnetic radiation and lose energy. Electrons moving inside atoms would be constantly accelerating, especially if they followed curved paths. This meant that electrons should continuously radiate energy, slow down, and spiral into the positively charged center of the atom. If this were true, atoms would collapse in a tiny fraction of a second. Matter, as we know it, would not exist. Clearly, this prediction contradicted reality because atoms are stable and matter persists. Another growing mystery came from spectroscopy, the study of light emitted and absorbed by substances. When elements were heated or excited, they did not emit light at all possible wavelengths. Instead, they produced very specific lines of color, known as spectral lines. Hydrogen, the simplest element, showed a particularly simple and well-defined pattern. Classical physics could not explain why atoms emitted only certain frequencies of light rather than a continuous spectrum. This selective behavior hinted that something fundamentally discrete was happening inside atoms. The problem deepened with studies of thermal radiation. Experiments on blackbody radiation revealed that classical theories predicted an infinite amount of energy at high frequencies, a result famously known as the ultraviolet catastrophe. This was another clear sign that classical physics was failing at microscopic scales. In 1900, Max Planck introduced the idea that energy is emitted in discrete packets, or quanta, as a mathematical trick to fit experimental data. Although Planck himself was hesitant about the physical meaning of this idea, it planted the first seed of a new way of thinking. Albert Einstein pushed this idea further in 1905 by explaining the photoelectric effect using light quanta, later called photons. His work suggested that energy exchange at small scales was not continuous but quantized. While this helped explain certain experiments, it created tension with classical wave theories of light and did not yet solve the atomic stability problem. The atom remained an unresolved puzzle, suspended between old laws that no longer worked and new ideas that were not yet fully formed. Meanwhile, experimental evidence continued to challenge existing models. In 1911, Ernest Rutherford's gold foil experiment delivered a dramatic blow to Thomson's plum pudding model. By observing how alpha particles scattered off thin metal foils, Rutherford concluded that atoms contained a tiny, dense, positively charged nucleus at their center. Most of the atom was empty space, with electrons somehow occupying the surrounding region. This nuclear model explained the scattering results beautifully, but it made the stability problem even worse. Electrons orbiting a dense nucleus should radiate energy even more rapidly, leading to an even faster collapse. By this point, the atomic problem had become impossible to ignore. The atom clearly had internal structure, electrons were real, and nuclei existed, but no classical model could explain how these components fit together in a stable way. Spectral lines, radiation behavior, and experimental scattering all pointed toward a deeper, hidden order that classical physics could not describe. Physicists found themselves in a strange position. On one hand, the laws of classical physics had been confirmed again and again in the macroscopic world. On the other hand, when applied to atoms, those same laws led to absurd predictions. The atom seemed to obey a different set of rules, but no one yet knew what those rules were. Theoretical physics was entering a period of uncertainty and creative tension. This uncertainty was not merely technical, it was philosophical. Classical physics assumed continuity, determinism, and smooth motion. Energy could vary by any amount, and particles followed well-defined paths. The atomic evidence suggested discreteness, sudden jumps, and restricted behavior. Accepting these ideas required abandoning deeply held assumptions about how nature worked. Many physicists were reluctant to take that step. By the time Niels Bohr began thinking seriously about the atom, the stage was set for a revolution. The failures of existing models were clear, the experimental evidence was overwhelming, and the need for a new framework was undeniable. The atomic problem before Bohr was not just a missing detail in an otherwise complete theory. It was a fundamental crisis that exposed the limits of classical physics and demanded a bold, imaginative response. Bohr's contribution would emerge directly from this crisis, shaped by the unanswered questions and unresolved contradictions that defined the state of atomic theory before his groundbreaking work. The crisis surrounding the atom deepened. the scientific community entered a period of uneasy transition. The old frameworks still worked astonishingly well for large-scale phenomena, yet they repeatedly failed when confronted with the atomic world. This contradiction created a strange intellectual atmosphere in which confidence and confusion existed side by side. Physicists were not short of data or experiments. What they lacked was a coherent way to interpret them. The atom had become a battleground where observation and theory refused to agree. One of the most troubling aspects of this situation was the growing gap between physics and chemistry. Chemists had long used atomic ideas successfully to explain reactions, bonding, and molecular structure. The periodic table itself hinted at an underlying order in atomic behavior. Elements displayed repeating patterns in their chemical properties, suggesting that atoms had internal arrangements that followed specific rules. Yet physics could not explain why these patterns existed. The structure of the atom, which clearly determined chemical behavior, remained hidden behind equations that produced contradictions instead of clarity. Electrons, once discovered, quickly became central to this mystery. They carried electric charge, had measurable mass, and behaved predictably in electric and magnetic fields. Outside the atom, their motion could be described using classical mechanics. Inside the atom, however, those same rules led to disaster. If electrons orbited the nucleus-like planets around the Sun, classical physics insisted that they must lose energy. The very image that made atoms easier to visualize made them impossible to sustain. This failure was not subtle, it was catastrophic. Attempts were made to rescue classical ideas by modifying details rather than abandoning the framework altogether. Some physicists hoped that unknown forces or complex interactions might stabilize electrons within atoms. Others speculated that the ether, once believed to fill all space, might play a role in atomic structure. None of these ideas survived serious scrutiny. They either contradicted experiments or introduced assumptions that could not be tested. The deeper scientists looked, the clearer it became that patching classical physics would not be enough. Spectroscopy continued to be a powerful source of insight and frustration. Each element produced a unique spectral fingerprint, a precise set of lines that could be measured with increasing accuracy. These patterns were stable and reproducible, suggesting that atomic behavior followed strict rules. Yet no classical model could derive these rules from first principles. The frequencies appeared to come from nowhere, governed by formulas that worked but had no physical explanation. The atom seemed to speak in numbers that physicists could record but not understand. Hydrogen, the simplest atom, became the focal point of this struggle. Its spectrum followed a remarkably simple mathematical pattern, first described by Johann Balmer and later generalized by others. The elegance of these formulas suggested an underlying simplicity in atomic structure. Classical physics, however, offered no mechanism to produce such discrete regularity. This was especially disturbing because hydrogen, with only one electron, should have been the easiest case to explain. If physics could not explain hydrogen, what hope was there for more complex atoms? The discovery of the atomic nucleus intensified the problem rather than resolving it. Rutherford's model replaced a diffuse positive charge with a concentrated core, dramatically changing the picture of the atom. While this explained scattering experiments, it sharpened the instability issue. An electron orbiting a massive, positively charged nucleus would be subject to enormous acceleration. According to classical theory, it should radiate energy even more rapidly than before. The atom, under this model, was even less stable than in earlier ones. This realization forced physicists to confront an uncomfortable truth. The atom was not merely a small version of familiar mechanical systems. It was something fundamentally different. Concepts like orbit, trajectory, and continuous motion, so successful in astronomy and mechanics, seemed to lose their meaning at atomic scales. Yet abandoning these concepts felt like stepping into the dark. Physics had been built on them for centuries. The early quantum ideas introduced by Planck and Einstein offered hints, but not a complete solution. Quantization explained certain aspects of radiation and energy exchange, but it did not yet provide a full picture of atomic structure. Many physicists viewed these ideas as mathematical conveniences rather than statements about reality. There was resistance to the notion that nature itself might be discrete at its core. Accepting that energy levels or atomic states were quantized required a profound shift in worldview. Educationally and institutionally, physics was also under strain. Textbooks still taught classical theories as complete and universal. Students learned Newtonian mechanics and Maxwell's equations as the final word on natural law. Yet advanced research papers increasingly revealed anomalies and exceptions. Young physicists entering the field sensed that something was wrong, but they lacked a clear alternative framework. The discipline was ripe for transformation, but the direction of that transformation was uncertain. This uncertainty was reflected in debates and disagreements among leading scientists. Some argued that the apparent failures of classical physics were due to experimental limitations or incomplete calculations. Others believed that a deeper revolution was inevitable. Conferences and journals became arenas for these disputes, with no consensus in sight. The atom stood at the center of these arguments, a small object causing enormous intellectual turmoil. Philosophically, the problem of the atom raised questions about the nature of scientific explanation itself. Should theories describe reality as it truly is, or merely predict experimental outcomes? Classical physics had done both remarkably well for centuries. In atomic physics, prediction and explanation began to separate. Empirical formulas could predict spectral lines, but no one could say what electrons were really doing inside atoms. This gap unsettled many scientists who valued understanding as much as accuracy. The public image of physics also played a role. Physics was seen as the most exact and reliable of the sciences, a discipline that revealed the ultimate laws of nature. Admitting that its core theories failed at the atomic level threatened this image, yet the evidence was impossible to ignore. Experiments did not bend to theory. Theory had to bend to experiments. By the early 1910s, the atomic problem had reached a critical point. All the necessary pieces seemed to be on the table: electrons, nuclei, radiation laws, and precise experimental data. What was missing was a unifying idea that could bring these elements together without contradiction. The failure was not due to lack of intelligence or effort, but to the limitations of existing concepts. Physicists needed a new way to think, not just new equations. It was within this atmosphere of tension, uncertainty, and anticipation that a new generation of physicists began to emerge. They were less attached to classical intuitions and more willing to accept strange, counterintuitive ideas if they matched experimental facts. The atomic problem before Bohr was, in this sense, a necessary stage in scientific evolution. The contradictions were not obstacles to progress. They were signals that progress required a leap. The secrets of atomic stability were not hidden because nature was cruel or deceptive. They were hidden because the questions being asked were framed in the wrong language. Classical physics asked how electrons moved continuously through space and time. The atom responded with silence. It demanded a new language, one in which stability came not from balance of forces alone, but from deeper principles governing what was allowed and what was forbidden. Just before Bohr's intervention, physics stood on the edge of this conceptual transformation. The atom had exposed the limits of the old world, and forced scientists to confront the possibility that reality at its most fundamental level did not conform to everyday experience. The unresolved atomic problem was more than a technical issue. It was a turning point in the history of human understanding. The stage was fully prepared for a radical idea that would redefine stability, motion, and the very meaning of physical law. Before the idea of quantum theory entered physics, classical laws were trusted almost completely. They had explained the motion of planets, the behavior of projectiles, the flow of heat, and the nature of light with astonishing success. These laws were based on clear principles. Forces cause acceleration, energy changes continuously, and particles follow definite paths through space and time. When scientists first tried to apply these same principles to atoms, it felt natural and even unavoidable. After all, atoms were thought to be tiny mechanical systems, and classical physics was the science of mechanics. Yet this seemingly reasonable assumption turned out to be deeply flawed. The failure of classical physics to explain atomic stability was not a small technical error, but a fundamental breakdown. At its heart was the behavior of electric charges. According to classical electromagnetism, formulated by James Clerk Maxwell, electric charges create electric fields, and moving charges create magnetic fields. More importantly, an accelerating electric charge must emit electromagnetic radiation. This radiation carries energy away from the charge, causing it to lose energy over time. This principle was well tested and worked perfectly in countless experiments involving antennas, electric circuits, and radio waves. Inside an atom, electrons are negatively charged particles influenced by the positive charge of the nucleus. Any motion of an electron around a nucleus involves acceleration, especially if the electron follows a curved or circular path. Classical physics therefore made a clear and unavoidable prediction. Electrons inside atoms must continuously radiate energy. As they lose energy, their motion should slow down, causing them to spiral inward toward the nucleus. Eventually, they should collide with the nucleus, destroying the atom's structure. Calculations showed that this collapse would happen extremely quickly, in a tiny fraction of a second. This prediction alone was enough to signal a serious problem. Atoms are clearly stable. Matter does not collapse instantaneously. Tables, buildings, and human bodies exist because atoms maintain their structure over immense periods of time. If classical physics were correct at the atomic scale, the universe as we know it would be impossible. The contradiction was not subtle or debatable, it was absolute. Classical physics predicted that atoms could not exist, yet atoms were everywhere. Attempts to avoid this conclusion only made the situation worse. Some physicists suggested that electrons might not radiate energy under certain conditions, but this contradicted Maxwell's equations, which were among the most reliable results in all of physics. Others proposed that electrons might move in special ways that somehow avoided acceleration, but no such motion was consistent with known forces. The problem was not a missing detail, but a direct conflict between theory and reality. The instability problem was closely connected to the way classical physics understood energy. In classical theory, energy is a continuous quantity. A system can have any value of energy within a range, and changes in energy can be arbitrarily small. This assumption works well for macroscopic systems like swinging pendulums or rolling balls. When applied to atoms, however, it led to disastrous consequences. Continuous energy loss meant continuous decay, with no mechanism to halt the process at a stable configuration. Classical mechanics also relied on the idea of well-defined trajectories. Particles were assumed to have precise positions and velocities at every moment, and their future motion could be predicted exactly if these quantities were known. Inside an atom, this meant electrons should follow specific paths determined by forces from the nucleus. But no classical trajectory could produce stability. Every possible path involved acceleration and therefore radiation. The very clarity of classical mechanics became a liability at the atomic scale. Another major failure of classical physics appeared in its inability to explain atomic spectra. When atoms emit light, they do not produce a smooth range of colors. Instead, they emit light at specific, sharply defined frequencies. These spectral lines are unique for each element and remarkably stable. Classical physics predicted something entirely different. An accelerating electron spiraling into a nucleus should emit radiation over a continuous range of frequencies, changing smoothly as the electron's motion changed. There was no reason, within classical theory, for only certain frequencies to appear. This mismatch between prediction and observation was devastating. Spectroscopy was one of the most precise experimental sciences of the time. The frequencies of spectral lines could be measured with extraordinary accuracy, and their patterns followed clear mathematical relationships. Classical physics could neither predict these frequencies nor explain why the emission was discrete. It offered no reason why atoms should prefer certain energies or frequencies over others. The problem extended beyond emission to absorption as well. Atoms absorb light only at specific frequencies, corresponding exactly to the lines they emit. Classical theory would expect atoms to absorb energy gradually and continuously, responding to a wide range of frequencies. The selective behavior observed in experiments had no place in classical thinking. The atom seemed to have built-in rules that restricted its interactions with energy, rules that classical physics simply did not possess. Thermal radiation provided yet another example of classical failure, closely tied to atomic behavior. When physicists studied how hot objects emit radiation, classical theory predicted that energy output should increase without limit at high frequencies. This prediction, known as the ultraviolet catastrophe, was clearly wrong. Experiments showed that radiation intensity rose to a peak and then dropped off. This failure was not limited to atoms alone, but it pointed to a deeper issue. Classical physics could not correctly describe how matter and energy interacted at small scales. The underlying assumption shared by all these failures was continuity. Classical physics assumed that nature allowed smooth variation in energy, motion, and radiation. Atomic phenomena consistently suggested the opposite. They hinted at discreteness, restriction, and selectivity. Electrons did not behave like tiny planets losing energy smoothly over time. Instead, atoms behaved as if only certain states were allowed and all others were forbidden. Even the concept of force began to lose its explanatory power inside atoms. Classical stability often comes from a balance of forces, such as gravity balanced by motion in planetary orbits. In atoms, no such balance could be achieved using classical forces alone. Electric attraction pulled electrons toward the nucleus, but nothing in classical theory prevented them from falling inward. There was no restoring mechanism to keep electrons at fixed distances or energies. The failure of classical physics was also evident in its inability to connect atomic structure with chemical behavior. Chemistry relied on the stability of atoms and the regularity of their interactions. The periodic table revealed repeating patterns that suggested electrons occupied specific arrangements. Classical physics, with its continuous variables and unstable orbits, could not account for these patterns. There was no way to explain why atoms formed stable shells, or why chemical properties repeated periodically. As these problems accumulated, it became increasingly clear that classical physics was being pushed beyond its domain of validity. The laws that worked so well for everyday objects, and even for celestial bodies, were simply not designed to handle the atomic world. This realization was deeply unsettling because it challenged the idea that physics was a single, universal description of nature applicable at all scales. What made the situation even more difficult was that classical physics did not fail gradually. It failed spectacularly. Its predictions were not slightly off. They were fundamentally wrong. Atoms were predicted to be unstable when they were stable. Radiation was predicted to be continuous when it was discrete. Energy was predicted to diverge when it remained finite. These were not errors that could be fixed with better measurements or minor adjustments. Many physicists struggled to accept this conclusion. Classical physics was not just a set of equations, it was a world you built over centuries. Abandoning it, even partially, felt like betraying the foundations of science. Yet the atomic evidence left no alternative. Nature was signaling that the classical picture of reality was incomplete. The failure to explain atomic stability was therefore a turning point. It showed that understanding the microscopic world required new principles, not just refined calculations. It forced physicists to question assumptions that had once seemed self-evident. That motion is continuous, that energy can vary smoothly, and that particles always follow definite paths. The atom exposed the limits of intuition shaped by everyday experience. This failure did not mean that classical physics was wrong in general. It remained extraordinarily accurate in its proper domain. What it revealed instead was that physical laws have boundaries. Beyond those boundaries, new rules apply. Atomic stability was the clearest signal of this boundary, a clear message that the microscopic world obeys principles radically different from those governing the macroscopic one. By confronting this failure, physics opened the door to a new era. The inability of classical theory to explain why atoms do not collapse was not the end of understanding, but the beginning of a deeper one. It created the intellectual space in which new ideas could emerge, ideas that would redefine energy, motion, and stability itself. The collapse predicted by classical physics never happened in reality, but the collapse of classical assumptions at the atomic level was both real and necessary, paving the way for a revolutionary transformation in our understanding of nature. As the implications of classical failure became impossible to ignore, physicists were forced to confront how deeply their trusted principles were intertwined with everyday intuition. Classical physics was built on experiences drawn from the visible world. Objects move smoothly, energy flows gradually, and causes lead predictably to effects. These assumptions shaped not only equations, but the very language used to describe nature. When atoms refused to behave according to these expectations, the problem was not just mathematical, it was conceptual. One of the most unsettling realizations was that classical physics could not even define what stability meant at the atomic level. In the macroscopic world, stability usually arises from equilibrium. A ball resting in a bowl stays there because forces balance. A planet remains in orbit because gravitational attraction is balanced by motion. Inside the atom, no such equilibrium could exist using classical ideas. Electric attraction always pulled electrons inward, and there was no classical counterbalance capable of fixing them in place without energy loss. Stability, a basic and familiar concept, seemed to vanish when examined closely. This breakdown forced scientists to rethink the meaning of radiation itself. Classical theory treated radiation as a continuous wave emitted smoothly over time. In atomic processes, radiation appeared in sudden bursts at precise frequencies. Electrons did not seem to leak energy gradually as waves. Instead, atoms behaved as if energy exchange happened in distinct events. This clashed violently with classical electrodynamics, which had no mechanism for such behavior. The wave picture of radiation, so successful in optics and radio, seemed incomplete when applied to atomic phenomena. The idea of predictability also came under strain. Classical physics promised that if one knew the initial conditions of a system exactly, its future behavior could be calculated with certainty. Atomic experiments undermined this promise. Even when conditions were carefully controlled, atomic processes showed fixed patterns without revealing the underlying motion responsible for them. Spectral lines could be predicted empirically, but the path taken by an electron during emission or absorption remained unknowable. The classical ideal of complete predictability began to erode. Educational and theoretical traditions made this transition even harder. Generations of physicists had been trained to trust differential equations, smooth functions, and continuous change. Atomic phenomena demanded discontinuous jumps, sudden transitions, and restrictions that had no classical cause. Accepting these features required abandoning cherished tools and intuitions. For many, this felt like stepping outside the boundaries of science itself. The failure of classical physics also exposed a gap between mathematics and physical meaning. Classical equations often produced infinite or nonsensical results when applied to atoms, yet the mathematics itself was sound. This suggested that the problem lay not in calculation, but in interpretation. The equations were being asked to describe a world for which they were never designed. This realization marked a shift in how physicists evaluated theories. A theory could be mathematically elegant and experimentally successful in one domain, yet fundamentally wrong in another. Another deep consequence was the collapse of visual models. Classical physics relied heavily on visualization. Particles as points, forces as arrows, trajectories as curves. Atomic behavior resisted such images. Any attempt to draw electrons moving around a nucleus led directly back to instability and contradiction. The failure of visualization was disturbing because it challenged the belief that understanding required a clear mental picture. Atomic physics suggested that understanding might instead come from abstract rules rather than familiar images. The instability problem also highlighted the limitations of reductionism as it was then understood. Classical physics assumed that complex behavior could always be explained by analyzing simpler components. Atoms, however, did not behave like miniature versions of larger systems. Their stability did not emerge from smaller mechanical interactions in a straightforward way. This hinted that new principles could appear at different scales, principles that were not obvious extensions of classical laws. As debates intensified, some physicists began to suspect that the electron itself might not be a classical particle in the traditional sense. Its behavior inside atoms did not match that of a tiny charged sphere following Newton's laws. This raised uncomfortable questions about the nature of matter. If electrons were not classical particles, what were they? Classical physics had no answer, only increasingly strained assumptions. The failure to explain atomic stability also affected the interpretation of experimental data. Instead of asking how electrons moved, physicists began to focus on what could be measured: frequencies, energies, and intensities. This shift in emphasis marked a subtle but important change in scientific attitude. Explanation became less about mechanical pictures and more about consistent relationships between observable quantities. Classical physics, with its emphasis on trajectories and forces, was ill-suited to this new approach. This crisis reshaped the culture of physics. Younger scientists were more willing to question long-standing principles, while older ones often resisted. The divide was not simply about age, but about intellectual flexibility. Those willing to accept that classical physics had limits were better prepared to explore new ideas. The failure of classical theory acted as a filter, revealing who was ready to move beyond it. By exposing its own boundaries, classical physics inadvertently guided physicists toward what was needed next. The instability of atoms pointed to the necessity of rules that restricted motion and energy. The discreteness of spectra demanded allowed and forbidden states. The impossibility of continuous radiation suggested that change at the atomic level occurred in jumps. These were not solutions yet, but they were signposts pointing away from classical thinking. The inability of classical physics to explain atomic stability also changed how success in science was measured. Predictive accuracy alone was no longer enough. A theory had to be conceptually consistent with the phenomena it described. Classical physics could predict many things accurately, but in the atomic realm, it contradicted existence itself. This contradiction was unacceptable, forcing a reevaluation of what it meant for a theory to be true. As the classical framework continued to fail, the need for a new foundation became urgent. The atomic world demanded principles that did not arise naturally from everyday experience. Stability could no longer be explained by balance of forces alone. It required deeper constraints on what nature allowed. These constraints would eventually come to be expressed through quantization and new rules governing motion and energy. The collapse of classical explanations was therefore not a defeat, but a necessary clearing of ground. It removed false assumptions and revealed the shape of the problem more clearly. Atomic stability was not something classical physics could be extended to explain. It was something that required a fundamentally different approach. The failure itself was the lesson, teaching physicists that the microscopic world followed laws that could not be guessed from the macroscopic one. In the end, the inability of classical physics to explain atomic stability transformed physics at its core. It forced scientists to abandon the belief that one set of ideas could explain all scales of nature. It opened the door to a new way of thinking, one that accepted limitation, discreteness, and abstraction as essential features of reality. The atom, once seen as a simple building block, became the gateway to a deeper understanding of the universe, precisely because classical physics could not explain why it held together. Niels Bohr's revolutionary atomic model emerged as a direct response to the deep failures of classical physics. Instead of trying to force atoms to behave like miniature solar systems governed entirely by Newton's laws, Bohr introduced a bold set of ideas that fundamentally changed how scientists understood matter at its smallest scale. His model did not reject classical physics completely, but it placed strict limits on where and how classical concepts could be applied. At the center of Bohr's model was the idea that electrons could move around the nucleus only in certain allowed paths. These paths were not chosen arbitrarily. They were determined by precise conditions related to the electron's energy and motion. Unlike classical orbits, where an object could exist at any distance and with any energy, Bohr's allowed orbits were discrete. An electron could occupy one orbit or another, but nothing in between. This single assumption immediately addressed the problem of atomic stability. As long as an electron remained in one of these allowed orbits, it did not radiate energy, even though it was accelerating. This idea directly contradicted classical electrodynamics, but it matched the observed stability of atoms. Bohr proposed that each allowed orbit corresponded to a specific energy level. The electron's energy was fixed while it remained in that orbit, and no gradual loss of energy occurred. Stability was no longer explained by a balance of forces, as in classical mechanics, but by restriction. Nature simply did not permit electrons to exist in states that would lead to collapse. This shift from continuous possibilities to allowed states represented a profound change in scientific thinking. Motion inside the atom was no longer free and unrestricted. It was governed by rules that selected only certain outcomes. A crucial element of Bohr's model was the role of quantization. Bohr introduced a condition that limited the angular momentum of the electron to specific values. This condition had no basis in classical mechanics, but it ensured that only certain orbits were possible. By doing so, Bohr connected the atomic model to the emerging quantum ideas introduced by Planck. Energy was not exchanged continuously, but in discrete amounts, reflecting a deeper structure underlying atomic behavior. The most dramatic success of Bohr's model came from its explanation of atomic spectra. Bohr proposed that electrons emit or absorb light only when they jump between allowed energy levels. When an electron moved from a higher energy level to a lower one, it released energy in the form of light with a specific frequency. That frequency was determined by the difference between the two energy levels. This idea explained why atoms produce sharp spectral lines rather than continuous spectra. Each line corresponded to a specific transition between energy levels. For hydrogen, Bohr's model worked with astonishing accuracy. It reproduced the known spectral lines exactly and even predicted new ones that were later observed experimentally. This success gave strong credibility to his approach. For the first time, a theoretical model not only matched experimental data, but also explained why atoms behaved as they did. The mysterious numerical patterns observed in hydrogen's spectrum suddenly had a clear physical meaning. Bohr's atomic model also provided a new way to think about the relationship between theory and reality. He accepted that some classical concepts, such as electron orbits, could still be used, but only as approximations. Other classical ideas, like continuous energy loss, had to be abandoned entirely. This selective use of classical and quantum ideas marked a transitional moment in physics, bridging the gap between old theories and the fully developed quantum mechanics that would follow. Although Bohr's model was later shown to be incomplete and could not fully explain more complex atoms, its importance cannot be overstated. It demonstrated that atomic stability could be understood only by introducing quantum rules that restrict what nature allows. More importantly, it showed physicists that accepting counterintuitive ideas was sometimes necessary to uncover deeper truths. Bohr's revolutionary model did not just solve a problem, it changed the direction of physics, opening the path toward a new understanding of the atomic world. The idea of quantized energy levels and Electron orbits was one of the most radical departures from classical physics ever proposed. It challenged the long-held belief that energy and motion could vary smoothly and continuously. Instead, it introduced the notion that nature, at its most fundamental level, operates through strict limitations. Electrons inside atoms do not have complete freedom. Their behavior is governed by precise rules that allow only certain energies and forbid all others. In this view, an electron bound to an atom can exist only in specific energy states. Each state is stable and well-defined, and an electron can remain in it indefinitely without losing energy. Unlike classical motion, where an object gradually changes its energy due to forces or friction, the atomic electron does not slowly drift from one state to another. It either occupies a particular energy level or it does not. There are no intermediate possibilities. This restriction is what gives atoms their remarkable stability. The term orbit, in this context, does not mean a classical path in the familiar sense. While early models imagined electrons moving in circular orbits around the nucleus, the deeper significance lies in the allowed energies associated with those motions. The orbit is better understood as a condition that defines the electron's energy rather than a visible trajectory. The electron's motion is constrained in such a way that only certain values of energy are possible, and these values remain constant unless the electron interacts with its surroundings. Quantization also explains why electrons do not radiate energy while remaining in an allowed state. Classical physics would predict continuous radiation due to acceleration, but quantized states prevent this. Radiation occurs only when an electron transitions between energy levels. These transitions are not gradual processes. They happen suddenly as the electron moves from one allowed state to another. During this process, the atom emits or absorbs a fixed amount of energy, corresponding exactly to the difference between the two levels. This behavior introduces a new understanding of how atoms interact with light. When an atom absorbs energy, an electron can jump to a higher energy level. This requires a precise amount of energy. If the incoming light does not match the required difference between levels, the electron cannot make the transition. Similarly, when an electron falls to a lower energy level, it releases energy in the form of light with a specific frequency. This direct link between energy differences and light frequencies explains the sharp, well-defined spectral lines observed in experiments. The idea of quantized energy levels also reveals why different elements have distinct spectral signatures. Each type of atom has its own set of allowed energy levels, determined by the structure of its nucleus and the arrangement of its electrons. Because these levels differ from one element to another, the possible transitions and emitted frequencies also differ. As a result, every element produces a unique pattern of spectral lines, serving as a kind of atomic fingerprint. Beyond spectroscopy, quantization reshaped the concept of measurement in physics. It suggested that some physical quantities are not infinitely divisible. Energy, at the atomic level, comes in discrete units rather than a continuous flow. This idea was deeply unsettling at first, as it contradicted centuries of scientific thought. Yet repeated experiments confirmed it again and again. Nature seemed to prefer steps over smooth slopes when it came to atomic processes. Quantized energy levels also helped explain the periodic behavior of elements. The stability of certain electron configurations arises because lower energy levels fill first, and electrons tend to remain in the lowest available states. This ordering creates patterns in chemical behavior, linking atomic physics with chemistry in a way classical physics could never achieve. Stability, reactivity, and bonding all depend on how electrons occupy these discrete energy levels. While early descriptions used the language of orbits, later quantum theory replaced these with more abstract concepts, such as probability distributions. Even so, the core idea introduced by quantization remained unchanged. Electrons are restricted to specific energy states, and transitions between these states govern atomic behavior. The visual picture evolved, but the principle endured. The concept of quantized energy levels and electron orbits marked a turning point in science. It demonstrated that the microscopic world does not follow the same rules as the macroscopic one. Stability is not maintained through continuous motion and gradual change, but through strict limitations imposed by fundamental laws. This insight not only solved the problem of atomic stability, but also laid the groundwork for modern quantum mechanics, transforming our understanding of matter, energy, and the structure of reality itself. The explanation of atomic spectra and stability was one of the greatest achievements of early quantum theory, because it connected abstract ideas about energy with clear experimental evidence. For decades, scientists had observed that atoms emit and absorb light at very specific frequencies, producing sharp spectral lines rather than a continuous range of colors. These observations were precise, repeatable, and unique to each element, yet classical physics offered no convincing explanation. The new atomic ideas finally revealed why this selective behavior occurs and how it is directly tied to the stability of atoms. At the heart of this explanation is the relationship between energy levels and light. In an atom, electrons exist in specific, allowed energy states. As long as an electron remains in one of these states, the atom is stable and does not emit radiation. Stability is therefore not accidental. It is a direct consequence of restriction. The electron cannot lose energy continuously because there are no allowed states with slightly lower energy. This prevents the gradual collapse predicted by classical physics and ensures that atoms maintain their structure over time. Spectral lines appear when an electron changes its energy state. If an electron absorbs energy from an external source, such as light or heat, it can move to a higher energy level. This process requires an exact amount of energy, equal to the difference between the initial and final states. Light that does not match this energy difference passes through the atom without being absorbed. This explains why atoms absorb only specific frequencies and remain transparent to others. When an excited electron returns to a lower energy level, the atom releases energy in the form of light. The frequency of this emitted light is determined precisely by the energy difference between the two levels. Because these differences are fixed, the emitted light has a well-defined frequency, producing a sharp spectral line. Each possible transition between energy levels corresponds to a particular line in the spectrum. The collection of all such transitions forms the unique spectral signature of the atom. This mechanism explains the remarkable regularity observed in hydrogen's spectrum. Hydrogen has only one electron, making its energy levels relatively simple. The pattern of its spectral lines follows exact mathematical relationships, which arise naturally from the structure of its energy levels. What once appeared as mysterious numerical coincidences are now understood as direct consequences of allowed and forbidden states within the atom. The connection between spectra and stability is profound. The same rules that prevent electrons from spiraling into the nucleus also determine how atoms interact with light. Stability and radiation are not separate phenomena, but two sides of the same principle. Atoms are stable because electrons are confined to specific energy levels, and atoms emit or absorb light only because electrons can transition between those levels. This understanding also explains why atoms can store energy. When an electron is promoted to a higher energy level, the atom remains in that excited state for a certain time without immediately releasing energy. The existence of stable excited states allows atoms to participate in a wide range of physical and chemical processes. Without such states, phenomena like lasers, fluorescence, and many chemical reactions would not be possible. Different elements produce different spectra because their energy level structures differ. The charge of the nucleus and the interactions among electrons shape the allowed energy levels in each atom. As a result, the possible transitions vary, leading to distinct patterns of spectral lines. This makes spectroscopy a powerful tool for identifying elements in laboratories, stars, and distant galaxies. By analyzing light alone, scientists can determine the composition of objects across the universe. The explanation of atomic spectra also marked a shift in how physicists understood measurement. Instead of focusing on unobservable electron motions, attention turned to measurable quantities such as frequencies and energies. This emphasis on observable results helped shape the development of quantum theory and clarified what it means to explain a physical phenomenon. Ultimately, explaining atomic spectra and stability showed that nature at the atomic level operates through discrete rules rather than continuous processes. Light is not emitted because electrons gradually slow down, but because they undergo specific transitions between allowed states. Stability is not maintained by constant motion, but by restriction. This insight resolved long-standing mysteries and provided one of the strongest pieces of evidence for the quantum view of the world, firmly establishing a new foundation for modern physics. Impact of Niels Bohr's ideas on modern quantum theory cannot be overstated, as his work laid the groundwork for a complete transformation of physics. Before Bohr, the atom was an enigma, defying classical explanation and presenting contradictions that seemed insurmountable. His revolutionary approach introduced a new way of thinking, showing that the microscopic world follows rules fundamentally different from those governing the macroscopic world. By combining empirical observation with daring theoretical innovation, Bohr reshaped the path of physics and set the stage for the development of quantum mechanics. One of Bohr's most significant contributions was his insistence on the principle of quantization. By proposing that electrons could only occupy certain discrete energy levels, he provided a framework for understanding atomic stability. This concept directly challenged the classical notion of continuous motion and energy, forcing physicists to reconsider the basic principles that governed matter. Quantization introduced a profound shift. At microscopic scales, not all outcomes are allowed. Only specific states are possible, and these states define the behavior of the system. This idea would become a cornerstone of quantum theory. Bohr's work also highlighted the importance of the correspondence principle, which states that the behavior of systems described by quantum theory must converge with classical predictions in limit of large quantum numbers. This principle bridged the gap between the familiar macroscopic world and the strange microscopic one. It reassured physicists that classical physics remained valid where it had always worked, while providing a clear pathway to understand deviations at atomic scales. This approach exemplified Bohr's unique blend of theoretical daring and respect for empirical reality, and it guided later developments in quantum mechanics. The introduction of discrete electron transitions to explain spectral lines was another profound impact of Bohr's ideas. Spectroscopy had long presented a puzzle, with atoms emitting light only at specific frequencies. Bohr's explanation, electron jumps between energy levels, showed that quantized states were not merely abstract constructs, but had direct, observable consequences. This connection between theory and experiment became a guiding principle for quantum mechanics, emphasizing that successful theories must account for measurable phenomena, not just mathematical elegance. Bohr's model also inspired the development of wave mechanics and matrix mechanics, the two complementary formulations of quantum theory introduced in the 1920s. While Bohr's initial ideas were semi-classical, treating electrons as particles in fixed orbits, they suggested the existence of rules governing microscopic systems that could not be derived from classical laws alone. This opened the door for Werner Heisenberg, Erwin Schrödinger, and others to formulate more complete theories that incorporated the probabilistic nature of quantum behavior, wave functions, and operator mechanics. Bohr's insights acted as a bridge between the old and new physics. Furthermore, Bohr's ideas influenced the philosophical understanding of science itself. His complementarity principle, though formulated later, emerged naturally from his early atomic work. It emphasizes that certain properties of quantum systems, such as particle, like and wave-like behavior, cannot be observed simultaneously with full precision. This principle challenged the classical view of an objective, deterministic reality, and introduced the notion that observation and measurement play a central role in defining physical phenomena. Bohr's work encouraged scientists to question deeply held assumptions about reality, causality, and determinism. Bohr's impact also extended to practical applications. Understanding atomic structure and energy levels enabled advances in spectroscopy, chemical analysis, and later technologies such as semiconductors and lasers. By revealing the rules governing atomic behavior, Bohr's ideas allowed scientists to manipulate matter at the quantum level. This was the foundation for the explosion of developments in atomic physics, nuclear physics, and quantum chemistry that followed throughout the 20th century. Lastly, Bohr's intellectual legacy inspired a generation of physicists to explore the counterintuitive world of the very small. He demonstrated that it is possible to make sense of phenomena that initially appear paradoxical by thinking creatively, respecting experimental evidence, and being willing to challenge classical assumptions. His work exemplified a balance between imagination and rigor, showing that progress often requires both bold hypotheses and careful testing. In conclusion, Niels Bohr's contributions profoundly shaped modern quantum theory. By introducing quantized energy levels, explaining spectral phenomena, and connecting microscopic and macroscopic behavior, he transformed our understanding of the atom. His ideas influenced the formulation of full quantum mechanics, altered the philosophical interpretation of physics, and paved the way for countless technological advances. Bohr's vision showed that stability and behavior at the atomic scale are governed by rules fundamentally different from classical expectations, and in doing so, he redefined the possibilities of scientific thought. The lasting legacy of Niels Bohr in atomic physics extends far beyond the specific details of his atomic model. His work not only solved critical problems of his time, but also fundamentally changed the way scientists understand the microscopic world. Bohr's influence can be seen in the conceptual framework of modern physics, in the methodologies adopted by generations of researchers, and in the practical applications that shape technology and daily life. His legacy is both intellectual and cultural, reflecting a profound shift in the approach to scientific inquiry. One of the most enduring aspects of Bohr's legacy is his introduction of quantization as a fundamental principle of nature. Before Bohr, the idea that energy could exist only in discrete amounts was revolutionary, almost heretical. By showing that electrons occupy specific energy levels and that transitions between these levels explain observable phenomena, Bohr provided a new lens through which to view matter. This principle became a cornerstone of quantum mechanics, influencing the work of Werner Heisenberg, Erwin Schrödinger, and Paul Dirac. Quantization, once a radical idea, is now a standard tool for understanding phenomena from atomic structure to solid-state physics. Bohr's model also left a lasting mark on the methodology of physics. He demonstrated that theoretical creativity must be balanced with experimental evidence. The success of his model came from its ability to explain observed spectral lines, not merely from mathematical elegance or analogy to familiar systems. This approach, anchoring bold theoretical proposals in empirical observation, became a guiding principle for future physicists. Bohr's insistence on connecting theory with experiment helped establish a rigorous framework for validating scientific ideas, a practice that remains central to all branches of physics today. Another aspect of Bohr's legacy lies in the conceptual tools he provided for understanding atomic behavior. By introducing discrete energy levels and the notion of electron transitions, he laid the groundwork for a new way of thinking about matter. His ideas helped bridge the gap between classical physics and the emerging quantum framework, offering a stepping stone toward more sophisticated theories. Even though later developments, such as wave mechanics and quantum electrodynamics, refined and expanded upon Bohr's model, the fundamental insights he introduced, energy quantization, atomic stability, and spectral explanation, remain embedded in the foundation of modern physics. Bohr's influence extended beyond pure theory into practical applications. Understanding atomic structure has led to technological advances that shape contemporary life, from lasers and semiconductors to medical imaging and quantum computing. Spectroscopy, which relies on the principles Bohr elucidated, has become a vital tool in chemistry, astronomy, and materials science. By clarifying how electrons behave in atoms, Bohr enabled a cascade of discoveries and innovations, demonstrating that foundational science can have profound and lasting technological impact. Philosophically, Bohr reshaped how scientists think about reality. His early work on the atom hinted at the limitations of classical determinism, foreshadowing the complementarity principle he later formulated. Bohr's insights encouraged a recognition that observation influences the phenomena being studied, a perspective that challenged deeply held assumptions about objectivity and predictability. This shift in thinking has influenced not only physics, but also broader philosophical discussions about the nature of knowledge, measurement, and reality itself. Bohr also left a legacy as a mentor and collaborator. He founded the Institute of Theoretical Physics in Copenhagen, which became a hub for some of the most brilliant minds of the 20th century. Scientists from across the world came to work, discuss, and debate at Bohr's Institute, fostering a culture of open inquiry and intellectual exchange. The environment he cultivated helped shape the careers of many key figures in quantum mechanics, amplifying his influence across generations. Through his leadership and guidance, Bohr created a community that advanced the frontiers of science and encouraged rigorous but imaginative thinking. Finally, Bohr's work symbolizes the courage to embrace counterintuitive ideas. His atomic model challenged deeply entrenched notions of motion, energy, and stability, yet he pursued it because it aligned with experimental evidence. This willingness to question foundational assumptions and accept revolutionary concepts serves as an enduring inspiration for scientists and thinkers. Bohr's legacy is a testament to the power of combining creativity, evidence, and rigorous reasoning to advance human understanding. In conclusion, Niels Bohr's legacy in atomic physics is profound and multifaceted. He introduced quantization, explained atomic stability, and connected theoretical ideas with experimental observation. His work shaped the methodology, philosophy, and applications of modern physics, while fostering a vibrant scientific community. By challenging classical assumptions and embracing a new understanding of the microscopic world, Bohr transformed not only atomic physics, but the very way humanity approaches the nature of reality, leaving a lasting imprint on science and society